Hello, my name is Carol Leibel, and today we're going to examine the normal distribution in AP biology. In experimental science, observations and measurements are made. Each measurement represents a piece of data, if you will. When multiple measurements are made or data is collected, one might want to analyze the data to determine trends and conclusions. There are two different types of data. For example, if you're measuring the amount of oxygen being consumed by respiring peas at two different temperatures, that's continuous data. On the other hand, if you are counting the number of males versus females, that's discrete data. Today, we want to focus on continuous data. One of the things you might want to do with all that data you're collecting is you might want to determine an average. Well, in statistics, there are three different ways you can average things. You can determine a mean, a median, or a mode. So let's talk about how you determine a mean. A mean is an average set of numbers or calculated to a central value. The way that you will do this is to sum the numbers and then divide by the number of values used. On your AP biology formula sheet, this is the way that it will appear. Now, this little symbol right here means to sum up. Xi means all the values you're working with. And instead of simply saying divide it by n, it turns around and it says multiply it by 1 over n. So let's suppose in AP biology, you want to know your average and you have 4 grades. The first grade that you have was a 55 on an assignment. The next grade you did much better and you received a 92, and then a 77, and then an 86. So how would you determine the mean? Well, according to this formula, you're going to sum it up, which equals to a value of 304. You're now going to divide it by how many grades you have, which is 4. So the mean, or the average, if you will, is going to be equal to a 76. Now, how do you determine the other two types of averages? Well, the median is the middle number in a sorted list of numbers. To find the median, the first thing you have to do is place the numbers in an order from the smallest value to the largest value. And then you need to find the middle number. So here we have a list of numbers. First thing to do is to put them in order from smallest to largest. And then in this case here, you find the middle value, which is 15. And so the median value is 15. What if we turned around though, and if we did not have an odd number, if we had a 32 here, and so now 15 and 16 are our middle values because we have an even number. What you would do then is add them up, divide by 2, so the median then for this list is 15.5. Now, to find the mode is a value that appears most often in a list of sorted numbers. So if we take this particular list and we put it in from largest to smallest, from smallest to largest value, we will notice that there are more 13s than any other number. So 13 is the mode, whereas 14 is our middle value, so that's the median. And when you add it all up and divide it by the number of values you're working with, the mean is 15. So we have an example here in which someone has measured the high temperature for 9 days straight and recorded this. What I would like you to do now is determine the mean, the mode, and the median. All right, so what you should have found out is that to find the mean, you're going to have to sum this all up and the sum is 537. You did this for 9 days, so you're going to divide that by 9, so the mean is 60. Now, you put them in order from the smallest value to the largest value. You have 9 numbers. 5 is the middle number, or day 5 was the middle day. So the temperature on day 5 was 63, so 63 is your median value. The temperature that appears most often is 68, so 68 is the mode. Let's suppose then that you're doing this for 365 days, and you want to consolidate your data to determine trends, if you will. You may want to make something called a frequency distribution table, which means how often do certain measurements occur. Once you make a frequency distribution table, then you may want to make an illustration using a histogram, which is a type of a bar graph that illustrates a frequency distribution. All right, so for example, you may want to find out if you're doing this for 365 days, you may see that for a temperature of 68, there were 15 days that it was 68. And maybe for a temperature of 69, there were only 5 days. And so you would make this wonderful table, and you would have your temperatures, and you would then put down the frequency. Okay? The temperature, and then the number of days, and so forth. Once you do that, then you would go ahead and make a histogram, and on that histogram, you may want to turn around and group your temperatures into values of 10. And so when you do that, you make something called a bin. When there are too many data points to make individual bars, the data is grouped together in increments in a particular range. Those increments are called bins. So in this case here, I would have a bin, and I would have 0 to 10 is my first bin, and then I would have 11 to 20 degrees, and then I would have 21 to 30 degrees. So this here would be my temperature. Over here, it would be how frequently were there days between that bin. So maybe 0 to 10, I had maybe 10 days, maybe 11 to 20 in that range, I had 16 days, and maybe I had 32 days in this area, and so on. And so that's what a histogram would basically look like. So looking at our example, we had 9 days, and we're going to use a bin of using 5 degrees. So we had 1 day in which the temperature was between 45 and 50. We had 3 days in which the temperature fell between 51 and 55. There were no days between 56 and 60. We had 1 day between 61 and 65, and we had 4 days, so the temperature was between 66 and 70. So now I've made my frequency distribution table. The next thing I'm going to do with this data is I'm going to make a histogram. So this is what the histograms would look like. Now the top histogram is kind of crude, and it's a draft, if you will, made with Excel. Some things that we would have to change on it is, first off, we have the word histogram up here, and we want to go ahead and replace that with the title. Down here it has bin, and we would like to replace that with what we're really measuring. We're measuring temperature in degrees Fahrenheit. You also notice that there's a space between the bars. If it's a true histogram, those spaces would disappear, and they would be right up next to one another. Okay, and then we would make our bars. Okay, we have 1 day between 46 and 50 and go through and make our little bars illustrating our distribution of temperatures, the number of days, how frequent those temperatures occurred. That's a histogram. All right, so here's another example. We have a student who wanted to measure the mass of 300 mung beans to the nearest thousandth of a gram to see if there's any variation in their mass. Now, looking at this beautiful photograph of mung beans, it appears that there's variation. I can see some small mung beans and some large mung beans, and they have different colors, and sometimes their shape's a little bit different. Um, so I would suspect that there is going to be some variation in their mass. So this particular student started to measure the mung beans. And once he started measuring them, he noticed that, oh my gosh, there's just so many different masses that I'm going to have to make some bins. And so this is what the student did. He used little vials and he decided that he would make a bin, and technically the bin that he used was starting at 0.050, and he measured that to 0.059, and he called that the 05 bin. And then the next bin was 0.060 to 0.069. The next bin was 0.070 to 0.071. The next one was 0.79, sorry. The next bin was 0.080 to 0.089, and last but not least, 0.090 to 0.099. And as he measured them, then he placed them into these vials so that he could just simply count the number of beans in each one of these vials to determine the frequency and make the histogram. And if you're looking at that, it's like, you can see that there are some beans that are small. There are some beans that are large, but the majority of beans are going to be found right here. And that there does seem to be an average, if you will, between 0.060 and 0.079. All right, once the bins were created and the beans were counted, then this is the histogram that was created. Each bar represents a bin from 0.01 to 0.019 grams. And what you'll notice is that right here, this seems to be the central value. And there are some beans that are very small and there are some beans that are very large, but the majority of beans are just in the average. It reminds me of Goldilocks and the Three Bears, and that this would be the mean, if you will. Now, let's look at this shape of this graph, if you will. If the number of data points are plotted on a histogram, and if we could turn around and smooth that histogram out, and the majority of the points lie close to the average or the mean, and as we go in either direction from that mean, we see that the number in those bins decrease, you get something that forms a bell-shaped curve. And that bell-shaped curve and that frequency distribution is a special type of frequency distribution called a normal distribution. And if you have something that forms a normal distribution, then what we find out is that the mean, the mode, and the median should all occur in the same place and have the same value, which would be right there. Now, many things, when you measure them and you plot them and you look at the frequency distribution, they tend to approximate a normal distribution. I really love this picture. It's a picture of World War I soldiers that are arranged in rows according to height. So over here on this end, we have some soldiers that are kind of short. And over here, we have some soldiers that are kind of tall. And then right here is where we would find our mean, if you will. And if you were to draw this, you would find something that looks like a bell-shaped curve, and it would form a normal distribution. Now, it's not perfect because, for instance, that row right there is a little short when it could be a little, or this one here is a little bit taller, if you will. But at any rate, if you had like 10 times the number of soldiers, then this would smooth out even more, forming a true normal distribution. There are many traits like height and weight and IQ that when you measure them will form a normal distribution. Here's a couple examples from a college biology book. And in this case here, we're looking at what time of year certain bullfrogs mate. Well, this particular bullfrog will start mating in March and end up its mating in the end of April. But the majority of wood frogs, they all mate about the third week of March. That is business for wood frogs. On the other hand, the pickerel frog, there are some that mate in late May. There are some that mate in early May and early April, but the majority of them mate around May 1st. And so what you're looking at is a normal distribution for the mating times for these four different types of bullfrogs. Here's another example of a characteristic forming a normal distribution. You'll find this in a chapter in evolution, and we're looking at the color of snails. Now, some snails are very dark, but there aren't very many of them, and some snails are very light, but there's not very many of them. And then there are the majority of snails whose color seems to be right in between the dark and the light, and the majority of snails fall into that category, if you will. In terms of evolution, let's suppose that this color is the best color to be in this particular environment. So what would happen over time? Look what happens to our normal distribution. More and more snails are the middle color. And you have very few that are very dark and even fewer that are very light. And so our normal distribution takes a higher bell-shaped curve, but it's still a normal distribution, if you will. On the other hand, let's suppose that the dark snails are favored over the light snails. Over time, you would see a shift in this normal distribution as the population of snails would become darker over time. And then let's suppose for whatever reason you favor dark snails over dark snails and light snails over this medium color. Over time, you would actually get two normal distributions, and it would favor the dark and the very light over the medium color. So again, this concept of a normal distribution appears in your textbook. So let's go back and let's look at those mung beans we were talking about. You can see that, yeah, there are a few really heavy mung beans and there are a few that are really light, but the mean is between like 0.06 and 0.08. And what we get here is it approximates a normal distribution. All right, so now it's your turn. But this time we're going to divide the class in half, and you're going to work in groups of, I don't know, 2 to 4, depending upon your teacher. And you're going to be using these little cups, and you're going to be using bins. However, the bins that we're going to be using is going to be 0.05, and hang on just a 0.10, 0.15, 0.20, 0.25, 0.30, and so forth, okay? And you will continue until I think probably you get to 0.55. And now you're going to mass 30 sample seeds and you're going to put them in the correct container. And you're going to, of course, record your mass. You're going to now make a histogram based on the number of seeds found in each one of these cups. The question is, does it form a normal distribution? Turn around, and what we would like you to do is once you get done, we will turn around and combine your classroom bins. So we're going to turn around and have pinto beans versus black-eyed peas. And black-eyed peas and pinto beans are much larger than mung beans, so that's why we're using larger bins, if you will. All right, so take your 30 seeds, mass them, record the mass, and put them in the correct bin, and then collect class data and make a histogram, if you will. All right, now this is the kind of histogram that was made using the class data of 300 seeds, where we've got your black-eyed peas and your pinto beans. And what do you notice about these two histograms? Which group of legumes or seeds has more variation, your black-eyed peas or your pinto beans? Well, hopefully you said the pinto beans. The pinto beans has more variation than our black-eyed peas. And if you look at our normal distribution, you can see that the bell-shaped curve is more narrow and higher in the black-eyed peas than the pinto beans. So I want to show you an example of two different histograms. We have histogram 1 and histogram 2. Think of them as our black-eyed peas and our pinto beans. How are the two histograms alike and how are they different? And technically, yes, there's a space between the bars, but that is done just for clarity. All right, so how are they alike? How are they different? Hopefully, you said that histogram 1 has more variation, that we start at 1 and we go to 9. You can also see that if you were to make and try to smooth this out, that the normal distribution, the spread, if you will, there's a greater spread in histogram 1 than we're going to have in histogram 2. Histogram 2 only goes from 3 to 5. So they both form a normal distribution, but the variation is different between the two histograms. And what does their mean, their mode, and their median? In both cases, it's 5. Now, there's a concept called the range, and the range shows the variation in the data that you've collected. So the range is determined by taking the maximum value and minusing the minimum value. So the range here is 9 minus 1. So our range is 8. Here our range is 7 minus 3, or 4. So there's more variation in histogram 1 than there is in histogram 2. There's more spread, if you will, in histogram 1 than histogram 2. And they both form a normal distribution. So if you go back to what we were talking about with our black-eyed peas and our pinto beans, The range is greater with our pinto beans than with the black-eyed peas. Not every frequency distribution, though, will form a normal distribution. So if you look at histogram number 1, it has a bias to the left, okay, in this area, and it is not a normal distribution. Histogram 2 has a bias, if you will, to the right, and it does not form a normal distribution. And histogram number 3, you can't find any discernible trend at all, and it's hard to determine what's going on in histogram number 3. All right, so much for normal distribution. Our next little our next webinar is going to be on standard deviation. Hope to see you then. Take care. Bye.